Today we're going to dive into this world of special relativity. Uh, we're going to see the overview of special relativity in this video. And first of all, let's ask a question like, what if time ran differently for you than me? And what if motion being the very fabric of reality? These questions are going to be answered or put forwarded as a conclusion of the theory of special relativity. First, let us see the world before Einstein. Uh, Physics was seen in the framework of Newtonian or classical physics. The Newtonian worldview is just that there is an absolute space and absolute time, which are independent of one another, and which the space and time uh, are not affected by one another, and they are an absolute in a sense that every clock at every point of space will tick at the same rate, so that Newton formulated this idea of an absolute space and absolute time. And it seems obvious that we experience support this Newton's framework or the idea of absolute space-time unless we travel near the speed of light or have large gravitation. We cannot experience the effects of relativity in which shifts this idea of an absolute space and time. So that before Einstein, the world view was the Newtonian framework, in which it suggests an absolute space and absolute time, in which clock at at every point of space will tick at the same rate. So that in this notion we'll see that the absoluteness of time. But it's not without crux that there were some sort of limitation to the Newtonian physics. Due to this Maxwell's equation, we know that the speed of light was this number 3 to the 10 times to the 10 to the 8 meter per second, and it was constant in all frame of references. And in the classical notions, or the classical notion of waves, there should be some sort of a medium in which, in order to wave to traverse, wave is just something that is disturbance of a medium. So that there was an experiment called Michelson and Morley, which conducted to detect this so-called the medium of light, which the scientists called at that time was an ether, and they tried to detect the velocity of ether relative to this the speed of the earth in the space. They failed to detect the speed of ether, no matter uh, how how much they try. They just always get the constant the speed of light. If there is an ether, and if the earth is moving through the ether, there should be a variation in the speed of light in order to know that the speed of this ether according to the earth in the frame of work of the earth. But it was a historically failed experiment, but it just opened a new door to the new physics. And in 1905 there is a revolution. For Einstein, it was Annus Mirabilis, the miraculous years of Einstein, in which he published 4 consecutive papers in a single year. And that is because it was called the Annus Mirabilis of Einstein. And the papers were like on the Brownian motions, and the other one was special relativity. And there were some sort of postulates in relativity in which it says there was a constant, it states the constancy of speed of light, and also it was rejected the classical idea of ether, in which it was proposed to the speed of, to fill the gap uh, to the idea of this constant speed of light, and the wave should have some sort of medium to travel. and also it marked the birth of modern physics, in which special relativity is one of the pillars of modern physics, which is a quantum field theories, and this particle physics just have a foundation in special relativity. Core principles of relativity. There are two postulates introduced in the theory of relativity. The first one is the laws of physics are the same for all inertial frame of references. This is just the extension of the idea of Galileo's relativity. By the way, there is a formulation of Galileo's relativity before Einstein's. Galileo was the original author of relativity, which was in the framework of Newtonian physics. It assumed that the space and time are absolute, so that there should be some sort of addition of velocities according to the different frame of reference, maybe an addition or subtraction of velocity according to the different frame of references. So that these postulates have a consequence in which it states there is an absolute motion that exists according to the exists in the universe. One object seems to be traced according to some point of reference, but it is moving according to the other. So that this introduced this idea of no absolute rest. And the second postulate was constancy of the speed of light. Light always travels at 300,000 kilometers per second in a vacuum, and this speed stays constant no matter how fast the object moves. This speed should stay constant. We're going to say later that the space should be contracted or warped or contracted or linked in order to make this happen, that the speed of light should be constant according to the all moving and non-moving frame of references, inertial frame of references. No matter how much you move, even if you move at 99.999%, the beam of light or this will appear to move at c, or 300,000 kilometers per second. And the very other idea that is introduced by special relativity is that space-time is interwoven in Newtonian notion. Time and space are separate entities, in which when we graph them, they're going to be an x-axis and a y-axis, which are completely independent of one another. One is not dependent, or which the two are separate entities, which mean that no matter how fast you move, it does not affect the time. But in the idea of special relativity, they form a single fabric called space-time, in which there are no more separate entities, but interdependent, one affect the others. Now we see our universe to be four-dimensional in the framework of relativity. And also the other consequence is time also is dependent in the state of motions. The time, the rate at which the clocks tick will be dependent on the state of motions or the speed of the object. Time might appear slower if the object is traveling near the speed of light. And the other idea is events are located by four coordinates. As I've said before, that our framework to conceptualize the universe is four-dimensional. It's three of space and one of time. So that an event, where and when, these are going to be located, an event are going to be located in the four-dimensional framework or fabric called space-time. And the one who introduced this framework of space-time is Minkowski, which were a teacher of Einstein. And let us see the consequence of special relativity. The first one demonstrated as consequences time dilation. These concepts introduced that moving clocks tick more slower than the stationary ones. This is the effect of special relativity, in which as one increased the speed in space, it will reduce. The clocks will tick more slower than the stationary ones. This was illustrated in the light clocks, in which moving light clocks and stationary light clocks, on which the moving light clocks will form a kind of a triangular method than the stationary ones. And the formula, there is a formula in order to calculate it. We are going to see that there are two t's, and this gamma is calculated by can be calculated by using this demonstration of light clocks. And let us, for example, if you observe to grasp this idea of time dilation, when astronauts travel through spaceships to the moon and came back for an observer on Earth, it will see that the astronauts' clock will run slower than the clocks of the one who stays on Earth. And it's not merely theoretical idea, but that has an experimental proof. For example, we know muons and atmospheric particles, in which we have detected, or we have an experimental proof that they live longer when they move faster from the atmosphere down to the Earth. The second idea is length contraction. Moving object shrinks along the direction of motion. This length contraction happens according to the frame of reference of a stationary object, moving object relative to the stationary object. When an object moves near the speed of light, they seem to be contracted or become shrink or shorter for an object which is in a stationary. And the formula, as you have seen the screen, that there is a formula to calculate it, and the lengths affect lengths parallel to the velocity. If an object A is traveling toward the x-axis, it is the length of the object which is contracted is only on the parallel to the velocity or the direction of motion. So that if the object is traveling toward the x-axis, the length that's going to be contracted is going to be also in the x-axis. For example, assume that a train moving near the speed of light, which is 100 meters, might seem to be shorter, maybe 64, and some sort of other numbers, but it will appear to be shorter when it travels near the speed of light. And this is also demonstrated in particle accelerators. When particles are accelerated near the speed of light, this gigantic maybe these gigantic accelerators, which were 6 kilometers in circumference, might appear to be in meters for these particles which are moving really fast at the speed of light. The notion of simultaneity is also changed in the framework of special relativity, when two events that are simultaneous in one frame of reference might not be on another. To demonstrate this idea, assume that two parties are going to sign a treaty in a train, and there is an observer inside the trains, and there is an observer outside in a train station. And according to the observer inside the trains, the two parties are going to sign the treaty at the same time. But when the trains pass by the observer that is at the stations, one of the party that is signing the treaties might have to be signing before the other, so that simultaneity is not a single event is not simultaneous in two different frame of references. So that an observer on the train will disagree with the observer on the ground. This is also demonstrated in lightning bolt strikes. When somebody sees two lightning bolts striking at the same time, simultaneously on the grounds next to each other, but if he sees a lightning bolt striking inside a fast-moving train, if the train is moving really fast, near the speed of light, it will the lightning bolts will appear to be striking at different times, because the train is moving to other while leaving the one lightning strike. And these notions will also destroy the idea of absolute now, so that time and simultaneity also depends on motion.